Hydroisomerization is a special case of breaking and recreating bonds in order to influence the structure of a hydrocarbon to change it into its isomer. So our design will attempt to calculate the volume of a potential reactor based on the weight of a selected catalyst. So our desired reaction is shown here. It's the conversion of N-butane to isobutane. Some thermodynamic information is included here. Most of that information we got from NIST for isobutane and butane. Some undesirable reactions include cracking. However, because of our chosen catalyst, which was aluminum chloride, and the process conditions, and the fact that we were working with alkanes that aren't that large, this wasn't much of a concern. However, it is possible. The online ACS publications were the primary source of information for the design specifications needed for the project, so we got most of our information for this process. This flowchart here shows the combination of the distillation column with the reactor. This reactor is basically the reactor we're attempting to design. Because it is an adiabatic reactor, temperature and pressure is changing as material flows through it. So therefore, because the rate laws depend on temperature, the rate of reaction will be changing as the material flows through the reactor. So to account for that change, the rate laws were written in terms of activation energy and temperature to show how the rate changes with temperature. So there are multiple kinds of catalysts that could have been used for this kind of reaction. We use aluminum chloride because it has the highest activity. It's the highest activity paraffin isomerization catalyst available for the design. Using this catalyst along with this temperature and pressure decreased chances of cracking happening and also overpressures, which was a safety concern with usually is a safety concern with packed bed reactors. However, because of our process conditions and the catalyst we're using, it wasn't too much of an issue. So for our simulation, we included some plots that show how conversion changes with catalyst weight, as well as how temperature changes with catalyst weight. So first thing you notice is the profiles for temperature and conversion are pretty similar with respect to catalyst weight, and conversion and temperature seem to plateau at about 1 kilogram of catalyst of aluminum chloride. Conversion plateaus at about 0.4 and temperature at about 355 Kelvin. And that is basically our design. These kinds of reactions are commonly used in the petrochemical industry, trying to increase the efficiency of certain hydrocarbons, oils, fuels, things of that nature.